Hi, I'm back with the same three charges, but a very different sounding problem. In the last problem, we calculated the voltage at this point P. We could call it V, and you could maybe put a subscript P to mean that you're talking about the voltage at that point. And remember that voltage is the amount of energy a charge would have if we're at that point P. So we can write it like this: U for potential energy divided by charge. Voltage specifically is actually energy per charge. U, potential energy in units of joules divided by charge in coulombs gives you volts, joules per coulomb. So we worked out what the voltage was at point P, and now in this problem, let's see what it says. What is the speed of a particle number 4 a long time after it is released from point P? So we're going to put in a particle 4, positive particle, place it right there. It's a little hard to do that. I had to push to get it there because this voltage, this is a high voltage location. And I put that charge there and let it go. Notice that the mass of this new particle is also given, so that's going to be important. We're also given that these three particles are just held fixed for this problem. So to approach this, we first notice that there's a before and an after. We start with the particle here, we let it go, and then it's going to get repelled by these two other positive charges, kind of get attracted by this one. I'm thinking that maybe it'll just blast away like in that direction, approximately. We don't care which direction it goes in. We just want to know its speed at the end of the day. So whenever there's a before and an after, you should think about conservation of energy. You can write conservation of energy. I like to write it as energy total, ET, before equals energy total after. So we can say the initial energy equals the final energy, I and F for initial and final. That's one way of writing it. If you want to take this energy beforehand and break it down, then you can make some progress. So energy can be broken down into potential energy and kinetic energy. So let's do that. The energy beforehand, the initial energy, will be the initial potential energy, U, plus the initial kinetic energy. I'll just call it KE initial. Afterwards, all of that energy added up has to equal the total final energy. So UF is the final potential energy, and KEF is the final kinetic energy. Now in this problem, the particle starts off at rest. So what does that mean? You get to set something equal to 0, right? The initial energy, kinetic energy, is 0 because the initial velocity is 0. So we can set that equal to 0. Also, we're told that the particle will fly away and get very, very, very far away. After a long time, it's basically infinitely far away. It's so far away that its energy, its potential energy is 0. And potential energy depends on distance. So the farther away it gets, the lower that's going to get. So the final potential energy is going to go to 0. So that lets us final potential energy is going to go to 0, excuse me. So that's UF equals 0. And the final kinetic energy is what we'll have to work with. So the potential energy initially is the voltage that we had previously calculated times the charge. So let's write that down for U initial. V voltage times Q, and this particle has a charge, let's call it Q4. That's its initial energy. Its final energy will be all kinetic. And as you know, we can write kinetic energy as 1/2 the particle's mass times its velocity squared. And I'll write V final there. V initial was 0. And note this V is for velocity, not voltage. So now we can solve for the particle's speed or velocity after it gets a long ways away. You can just do some math here. Multiply through by the 2, divide by m. I would get 2V voltage, Q4, divided by the mass of the particle, m4, equals particle's velocity squared. And to now solve for velocity, you just take the square root of both sides. So we could write that as V equals the square root of 2, capital V, Q over M. So now you can plug in numbers. As you plug numbers in, you'll want to make sure you use consistent units, so include the units in the numbers as you plug them in. If you use all standard SI units, then you should get a velocity out in terms of meters per second. So you might need to do some unit conversions when you're doing a problem like this, but after you do them, you'll get a velocity in terms of meters per second. All right, and then you'll know how fast that particle shoots away after it started off with a certain amount of energy. By the way, I'll also say that this is exactly the same as the kind of problem you've already solved before in previous physics class. Imagine you are asked to figure out what the speed of some ball is that starts off on top of a hill and then it rolls down the hill. You would figure out its potential energy based on its height, use maybe U to represent that, and then set that equal to 1/2 mv squared, its final kinetic energy. And you need to know the mass of the ball. So it's exactly the same kind of problem.